Swayam Prabha. Digital India. Educated India.
Today, we will look into another of the protocol innovations that came into light because of the internet or the HTTP workloads called QUIC. QUIC, also pronounced QUIC, is a general-purpose transport layer network protocol that was initially designed by Jim Roskind at Google, and it started to take shape and got implemented around 2012 and deployed in the early versions of the Chrome. And as it grew, the experimentation broadened, and many of the web browsers, including the MS Edge, started to adopt it, and now we see it supported by almost all of the browsers that we use today. So it's important to understand a bit of background on why there was a need for a newer protocol called QUIC and what are the key things that it tries to address, at least in brief. So to understand that, we need to know what was the early internet like and what were the key protocols that existed. And when we look at the transport layer, it's primarily the two of the key protocols that shared the majority of the traffic. And when there was an analysis done in the early 2000s about what was the network traffic look like, and it was observed that more than 90% of the traffic was TCP, while rest of the 10% was shared amongst UDP and other kinds of protocols. So TCP being a prominent chunk in the internet at the transport layer. And the popularity was so because it tried to provide reliable communication over the best effort internet network or the IP layer, and it essentially built the congestion control and flow control, which were quintessential to ensure that multiple of the end users can reliably connect and access the services over the internet. And the other variant that was prominently used for majority of the services was the UDP, which basically was meant for very short independent message kind of a communications where you don't care as much about the loss, but you would be happy to retry and get the service done. So wherever you saw the potentials for low overhead and a pattern of query response would directly gel in this kind of a pattern. And that's where we saw the use of DNS, DHCP that tried to adapt UDP, while most of the internet services where packet loss and congestion were a common phenomena, they adopted for TCP to ensure reliable data transfer. And what eventually happened was this ossification of the protocol around the transport layer, where all the applications that we can think of, be it the web, VoIP, services, email, all of them try to rely on one or the other variants of TCP. And this is where another way to look at it was a protocol ossification that happened around TCP. And it was not that TCP was the best fit, but it was amongst all the services that you could rely on for reliable transmission, it served the key purposes. Hence, if we see TCP, the key characteristics that it provided was to ensure that it would provide for multiplexing and demultiplexing of the services. That means at the end hosts, we could run multiple of the TCP connections and ensure that different applications use use the same TCP stack but with different port numbers, so that you are able to get the services done for different applications. So I could run the mail service, I could run the web browser, I could run the FTP service. All of those could underlying use the same transport stack, and you would essentially multiplex and demultiplex the streams through when you process it through the IP and get it to the other end. And most importantly, as we see, that IP layer is best effort service, wherein there is no guarantee that the packets that you transmit would eventually make it to the other end. So you needed the controls of reliability. How would you ensure that the other end is existing, listening for the connection? And that's where the three-way handshake protocol of TCP played a major role. And then you may have diversity in terms of devices, which may have different rates at which they would serve. So you needed a flow control that ensured that the data that is delivered doesn't overflow the receiver and ensure that both are in sync with respect to the data exchange without trying to have lots unnecessarily over-transmit and fill the buffers. And also the ordering of the delivery, which ensures that the stream of bytes are correctly received at the sender, regardless of whatever the packet loss happen, the receiver is able to get back the order in which the packets are intended to work, made it all essential for TCP to be serving for majority of the applications. And likewise in the network, when we speak of congestions that can happen sporadically, you also wanted the mechanism to react to those congestions which were incorporated in the TCP. And this made a very strong case for why TCP dawned majority of the internet services to be the underlying transport protocol. However, at the TCP, it has its own set of challenges. So if we think of when we are transacting for a very small connection and we see that in order to make the transaction, we need the TCP handshake to go through. That means the three-way handshake of the TCP, that is SYN, SYN-ACK and ACK packet exchange between the sender and the receiver, is a mandatory precursor to ensure that we can even start before we start exchanging the data. And this, in many times, was a major issue, because if you see that I'm trying to exchange information over a 1 gigabit link for just of around few kilobits, then I'll be done in few milliseconds. But this TCP handshake through which the service that I'm trying to connect is around 10 to 20 milliseconds apart, then I'm spending at least almost one full round trip to get this initiation done. So I'm adding a lot more penalty in getting this service done. While with the UDP, on the other hand, we saw that it would just transmit the packets without caring whether the service is up or not. So you would see that you don't spend or have any overhead in handshake, but you don't guarantee that the service on the other side is there to even process your request. That was the other side of the challenge. So there were many works that came in the light of how to address this three-way handshake approach, and one of the nice works is in Conex 2011, that was TCP Fast Open, and it tried to analyze and say what's the real overhead that we really see with TCP. And it was shown in this plot here saying you are doing a simple search kind of a query, you are paying around 15 to 20% of the overheads that are coming for the initial handshake, while the image thumbs that are going to be put or the map tiles that you are getting or photos. In most of the requests, the cold request includes the three-way handshake overhead, while the other requests where you avoid the handshake overhead, you see that it reduces by more than 60-70% overheads. And this meant that whenever you are transacting for a small queries over internet, you are paying a very high penalty. Besides, when we add the overheads that are necessary for ensuring that you have an encrypted channel that is built by the use of TLS, you need additional handshakes to happen between the client and server to negotiate the cryptographic parameters and exchange of the certificates so that the two parties can trust and negotiate the keys through which they can send the encrypted data. And this further worsened the overheads that you would see that would add up or pile up for having this connection set up. And with TLS handshake, we are typically talking about almost 2 to 3 additional RTTs before even we could send or make a request. Hence, this was some way to be looked at to see how we can minimize these overheads. And the other aspect to think of when we see of TCP is, if I'm currently connecting to any of the websites, typically we expect multiple of the different kinds of data that are being glued would be downloaded. Even if I'm going for a simple web page, you have the HTTP connection, HTTPS connection, but that would essentially require you to get the HTML page, the CSS, the styling page, the associated scripts, and then any of the image contents or data that you would additionally have. So typical web connection would end up having multiple of the kinds of data that you would have them downloaded before you render such a page. So there were essentially the aspects of how would you handle downloading of multiple of these data, whether to make independent TCP connections or have it as one TCP connection on which the entire data is going to be transacted. And this was studied much in the early HTTP 2 times, and it was that, okay, every data that you want is in a way glued, and you want them to be treated as streams of data that could be either independent connections or could be served on a same connection. Like in HTTP 1.2 onwards, and you see in HTTP 2, you could basically have a stream of connections that could be run over different TCP connections. But if you open multiple of the TCP connections, you would end up having a lot more overhead at the client as well as the server, because now server and client have to maintain the state for all of these connections, and that would may not be as much a problem on the client, but on the server, which is going to serve many of the other clients, thus having multiple connections per client could become a bottleneck. And hence it was also thought about to say how you can basically multiplex a same TCP connection to carry different streams of data, that was streams within a single TCP connection. And this was in a sense to say that I could have a stream of bytes that would say what is a CSS content, or a style page, could have this another stream that would say what's the HTML content and start to get them downloaded within a single TCP connection. Rather than having a connection per object, you could basically have a single connection multiplexed for multiple of the objects that you would want to download as streams. But this introduced another critical aspect of what we call as head-of-the-line blocking. This again is a characteristic of TCP that we need to understand what this is and where the problems could lie. So if we try to look into the head-of-the-line blocking, let's consider just a very simple page that has two different kinds of objects that we want to download. And from the server side, it may be able to put the contents of one type and put the contents of other type of the object both in a same TCP connection. And what that means is network may write first the packet 1 and packet 2, which belong to a particular object, and then may try to write other data. But when it writes packet 1 and packet 2, on the application side of the client, you would basically be able to receive and read up till packet 1 and packet 2, because this is a sequence of stream of bytes that make up the TCP packet to be read. But now if suddenly that the network wrote packet 4 while skipping the packet 3, but consider packet 1, 2, 4 all belong to the same object. At this point, because TCP is byte ordered reception, it would not be able to read beyond packet 2 because it requires packet 3 to even start to look at packet 4. And this is what we term as head-of-the-line blocking. This is a genuine case if we need or if we have a scenario where packet 3 also belongs to the same object. But what if the packet 3 belongs to another kind of an object while packet 1, 2, and 4 are actually for one kind of an object and they are in sequence? Now TCP cannot distinguish between the two and it would just block even if packet 4 were the next sequence that you need after packet 2 for getting or fetching the object 1. So what this essentially means is we are blocked now because of the head packet, that is packet 3, not being there to make the sequence complete. And what this would mean from the application point of view is that browser is not able to render the object 1, which consists of packet 1, 2, and 4, which it already received, but because of the missing packet 3, which was for another object, but it is still not able to render the object 1. And when we see nowadays with the websites, typically we are having around 15 to 20 different kinds of objects that are going to be delivered. And if all of these are going to be done in a TCP sequence, and if any one of them in between changes its or have a loss, or we are not able to have a sequence, we are blocked for majority of the contents, even though we might have the full content that we may have for a given object. And this is a major problem that was to be worked out and see what options or what mechanisms could be built. And we need to think now in terms of what are all the ways that these could have been addressed. And several works stemmed, like we said, about the TCP Fast Open in 2011 that tried to focus primarily on how you can abridge the RTT connection or the round trip time. And likewise, the attempts were made, especially from the web community, in terms of what other aspects could be worked out. And this is where basically the emergence of QUIC started. And if not, like what were all the other options that we had were also the considerations to think. And here you may see that if we have to change or tweak anything with TCP, you have to change the operating system kernel, because the entire network stack is where the kernel hosts this TCP stack, and you would have to change this kernel. And that also means then all the end hosts, and you have lots of diversity on operating systems kernels that reside on both the server side and client side, including variety of form factors, including the laptops, phones, all had to be changed. And that's a overwhelming task. And if anything in the TCP headers were to be changed, nowadays we said the network is full of middle boxes. And if the middle boxes are not able to understand the packets at the transport layer, if they are operating at a layer 4, there is no way that the packets would eventually run to their destiny. Hence, the updates on the middle boxes also to ensure that any changes on such a protocol at the network stack in the TCP layer at the transport means you have to also upgrade all of these essential middle box devices. And if the middle boxes, the by default rule, especially when you are security privy, is to say that if you are not able to recognize the kind of a packet, you simply drop it. What that meant is you run a situation where any tampering with the transport layer headers could essentially mean that packets get dropped silently somewhere in the network. Hence, a better alternative to say how we could work around and bring the concept to be within the realms of the TCP and UDP to facilitate or overcome these challenges were thought about. And now, what the engineers at the Google tried to realize is to say that why not just rely on UDP for the internet connections so that you get rid of the three-way handshake, but try to build a packet format on top of UDP at the application layer. So what it meant is like the key characteristics that TCP handles in terms of flow control, congestion control, and reliable byte stream in an ordered fashion of packet delivery. All of this, if it can be pushed to the application layer and keep the transport layer as simple as what a UDP does, just that is to exchange a message between the two ends. And this was the start of what we call as a QUIC, or which initially stood for an acronym, Quick UDP Internet Connections. And this work started in, like I said, around 2012 and 2013, and the Google Chrome was the first to start this kind of a service. And what it really tried to address were the two critical issues that we said, and there are many more other issues. Because of the other constraints, we limit to just these two issues to understand QUIC in this prospect. So first was to address the handshake problem. So if handshakes meant that there is a round-trip time overheads, there is a means that we want to cut down on them. And this means were supposed to be defined as a part of a newer protocol. And we know that UDP has no such overhead. So if we try to bring that on top of it and use at the application layer, we would try to build the intelligence to say how we can build the reliability over the UDP in one way, and how we can build the ordered delivery of packets over the UDP. And the third part is how we could also build multiple streams of data over a same UDP connection. And all of this in a way that, because UDP is an established network protocol and middle boxes would treat them as just the typical UDP connections, you would not have any issues or concerns of packet drops that would happen either at the middle boxes in anywhere in the network. So ticking all of these aspects, now the question in essence was how to build the handshake procedure so that you are able to ensure that you are able to negotiate and ensure the client server side of the window and parameters in terms of what data rate that you would want to send. And the second issue, like we just said, if there is a head of line blocking because of the ordering of the packets and byte streams within the TCP connection, how this can be basically decoupled so that you are able to ensure that ordering of the bytes for a particular object is maintained but not for the entire connection. Wherein if my connection is serving to send different objects, I want to ensure just the ordering of bytes for each of those objects. Not necessarily that when object 2 is sent, I want to look for any information that is tied with object 1 or object 3. Likewise. So we also wanted to have better priority management in terms of if I have the streams and if I have like a different kinds of data, which data I want to render first, so that I could prioritize sending that information over the same UDP channel to ensure that you get the data correctly in the order that you would want the browser to render. So all of these were the key design characteristics that led to the development of QUIC. And one more important aspect that we also want to bring with respect to QUIC is this primarily was thought in the lights of the HTTP workloads, where you had a browser as a client side and you're typically interacting or transacting with the HTTP server on the other side. And whenever we had this connections, we always thought of having a secure connection, and that's where the TLS also came in to provide the secure or encrypted connections. And now if we saw the earlier stack, what we would see is you have the TLS on top of TCP on the left hand side here. And if we now want to support the newer framework or a newer protocol, we also had to ensure that we support the TLS. But thus, when we see the TLS has a handshake which is done only after the TCP handshake is done. And this TLS handshake, in a sense, ensures that there is a server that is listening for your connection and you could establish a connection. So you can see that the TCP initial handshake in essence becomes redundant if we are able to ensure the same with the TLS handshake. And likewise, the only things that now we need to consider if we do this at TLS handshake is what are the initial negotiation parameters that TCP exchanges need to be done alongside with the cryptographic handshake. And this is where QUIC tried to incorporate both the TLS part of what handshake needs to be done and the transport side of the handshake to negotiate the parameters on the congestion control, the features that you would want, how do you want to ensure loss recovery, all of these parameters together with the encryption based handshakes that you would want to do. Hence, the way that QUIC stack was developed was to replace the transport layer TCP with UDP and replace the earlier versions of TLS with a newer version of TLS 1.3, which also supported for less RTTs to negotiate the cryptographic parameters. In fact, zero RTT in terms of exchange of the secure keys. If you already have the pre-shared keys, you could directly reuse. And these made TLS 1.3 a better fit for QUIC. And what QUIC readily tried to absorb was to use the TLS 1.3 as the encryption model and build the application layer protocol around TLS 1.3 and build it on the UDP transport. And the services that it provides again is to the other application layer on the above that is called the HTTP3. And in May 2021, all of these efforts got standardized and we have a series of RFCs starting from 8,999 to 9,000, almost 12 or 9,013, detailing about how the QUIC's operation should be and what are the ways that QUIC would work with HTTP3. And this also meant there was a need to change the ecosystem around it. That means if I'm trying to check and get the DNS parameters for a given connection, I should be able to get the DNS connection whether the server supports HTTP3, that is QUIC. And if it supports, then client and server could ensure that they can communicate directly over QUIC. And that also meant that there is a need for a DNS change. And there were alt services that were being updated to say that whether a server supports HTTP3 or not. And if not, you would fall back to using HTTP2 and use the standard TCP TLS model that you're seeing here on the left-hand side. And this is how the QUIC brought in a significant change in terms of how we could ensure the connections to come up. And what it essentially tried to address in case of when we consider the first issue of the TCP handshake and the latency overheads, it tried to bring what we call as the most common case of a zero RTT handshake. And that meant you had no overheads to pay and you could start exchanging the information right away without any overheads. And if that was in special cases, that if it were not to be possible, then it made possible of one RTT handshake where you would have to establish the connection with one RTT and then start exchanging the parameters. And this is much smaller than typical 3 RTTs that you have with the TCP TLS stack. And only in the cases very rarely where there is no support for the QUIC, and if client had started with a QUIC, you would have to fall back to the TCP connection. That meant you would go up to 2 RTT handshakes when you know that there is no support for QUIC. And this is what the most common case that we see with the traditional TCP, and it's still the same. And what other important aspect the QUIC also tried to address in trying to do it is because now you are trying to merge the cryptographic information within the first packet. You avoided the overheads of additional RTTs to negotiate the cryptographic parameters, especially the symmetric key that you would want to use for encrypting the session details. And with the TLS 1.3, it also facilitated to say that if I have a cached credentials, I could directly start to assume that the server would work with the credentials that I earlier shared in one of the connections and start using it. Because most often we would have the connection parameters, we are connecting to a particular site, we repeatedly connect over time. And if I can ensure that the keys are recycled over a large duration, let's say in an hour or so, then you could reuse the same keys to establish subsequent connections. And this is where the low latency handshake parts were realized through QUIC. So to quickly look up what it meant in the TCP and TLS 1.3 version, first you would have a SYN, SYN-ACK and ACK. That's basically the TCP three-way handshake. And once TCP handshake was done, you would have the TCP connection parameters that were exchanged, and then the TLS connection handshake would start with the typical client hello, server hello, and followed up by the exchange of the server certificate, which the client would authenticate, and client would verify that he's connecting to the right server, and then start the client side of the TLS negotiation, and eventually derive a key through which the entire session could be encrypted, and then start sending the packet request. And this is where we can see that it at least involves 2 RTTs and typically 3 RTTs to ensure that you have the TLS setup and TCP setup before we start and send the application data. But with Quick, because it operates at the application layer and relies on the UDP transport, we could merge basically the client hello with the initial parameters for a quick communication to exchange the application layer of the transport characteristics that we want at this point. And what this meant is you typically need 1 RTT to exchange the client hello, server hello, all the certificate negotiation, wherein encryption is done right from the end of the client finished. So you would have the entire encrypted session that is starting right after the client finished, which is where we can see that this is just 1 RTT overhead. And if we already have these connections that were being sent, or this certificates that were being exchanged with the server, you would have those cached within the client side. And for the next subsequent connection, you could reuse the same and start directly with the HTTP request using the same earlier cached quick parameters and just communicating that we are trying to establish a connection with these parameters with the server. And if the things are all sessions, parameters all seem fine, you could essentially have the server respond back, and this is where the 0 RTT overhead communications happen with Quick. And the second important aspect that Quick also tried to address is the head of the line blocking. And if we consider the reason why that happened with TCP is independent of the kind of an object that you transmit, every information that you pass in a TCP packet is sequenced as per the numbers that you would put. That means every byte belongs to just one stream or one stream of byte that you would exchange over TCP. And these bytes could refer to different objects, and that was for the user end to say what objects that this byte meant for. So now if we decouple this information and say, if we build the protocol with the packet data structure where we isolate the packet number, and this packet number essentially refers to the stream of connections that are happening over the Quick. And within this, I may support multiple of the frames. And what this means is I may send multiple of the packets, 1 to n, and within each packet, I may have packet 1 correspond to one of the frames data, packet 2 correspond to one of the frames data, and likewise. And within each of the frame, I want the sequence numbering. That means the offset information that is highlighted here would correspond to the actual sequence of bytes that you would need for a kind of an object. So if I say frame 1, it belongs to a particular object, I would want to ensure that this offset information is this sequence of streams that I want to build within that frame 1. While for frame 2, I could have a different packet number, immediate next packet number, send out packet frame 2. So then it doesn't matter whether the packets were really in sync or not, but what matters is whatever the packets that you receive, do they have the frames that are in sync or not? And this is a simple data structure that was being pulled to say that you isolate the streams from the packets that are going to be exchanged, basically decouple this information. And now we can ensure that applications look for and match on the offsets to build a stream of sequenced bytes for a given frame. So that way we can multiplex now multiple of the objects within a same connection. And this means that now streams will not encounter any of the head of the line blocking, as we have separate advertised window per stream for each of the connections, because the number that we are seeing for the frame offsets is the sequence of data that is for each stream. And also we could now say which frames have different priorities and embed the packets to ensure that these frames are going to be sent with different priorities. And this structured streaming mechanism at the Quick enables us to overcome head of the line blocking. So let's try to revisit the same example that we spoke about earlier and see how this would operate in the view of Quick. So if we had the packet 1, packet 2 that were sent, from the application you could read out packet 1, packet 2, and you're going to read packet 1, packet 2 also as a contiguous bytes for a stream 1, which refers to a particular orange object here to say that data is prepared. And then when the packet 4 is sent, although it is packet identifier is not in sequence, but within this packet, when you see the stream, which belongs to the same stream as the orange object, and the byte offset aligns with whatever the data that you had at this end, now you are able to basically take the entire orange stream, that is 1, 2, and 4, to view it as a single frame. And this ensures now that the browser can basically work out the 1, 2, and 4 together and render the object as you received the packet 4. And eventually when the packet 3 is received and you'll see that this is for another object, it could also take and build this sequence of the streams, or if that is contained object, it could also render. So essentially now this helps decouple of the stream sequence of bytes versus the packet sequence of bytes, ensuring that application can now be free of the head of the line blocking, utilize the same connection. You need not have to build multiple connections either, because each TCP connection or each UDP connection can now be viewed as different streams of connections that are operating in parallel. In essence, the streaming of the data is done per stream within the same QUIC or a UDP connection. And in fact, there were several other additionals that the QUIC brought in terms of saying how you could do better RTT management. How do you want to ensure when there is a packet loss? In TCP, you have to discard retransmissions from accounting for RTT estimation. But with QUIC, it also meant that it came up with the mechanisms where you could try to say how you could still be able to do better RTT estimation even in the events of packet loss. And it also introduced a swing bit, which was a very interesting aspect, but debated heavily as well in terms of having just one bit to ensure that you can do the RTT estimations without having to do much of the computation overhead. Because at one point when I send a window, I can set a bit to 0 for one window, one RTT, and in the next RTT I can spin the bit back from 1 to 0. So there were a lot of optimizations that were brought in from QUIC, and the deployment, although it started in the early 2014-15, now we see most of the internet traffic when we are especially transacting with any of the Google sites or any of the Chrome website, it tries to use QUIC to ensure that you are able to get better and faster connection. And what we can learn from the QUIC in a nutshell is that layering is a good aspect in terms of modularity, but it can hurt performance because of some redundancies that creep in, because TCP, TLS both had to do the handshakes, but TLS stacked on top of TCP could not proceed until the TCP handshake is done. And this also meant now doing the TLS handshake engendered the TCP handshake to be, in a sense, redundant. And although there were some key parameters that you would want to exchange for TCP, which could then be coupled with the cryptographic handshake. And this is where the QUIC tried to leverage the two and try to bring a handshake that essentially does both the aspects in one go. And it is also important to see how, when we layer and build, what are the side effects or the impacts that they bring in terms of the application metrics of latency, throughput at a macro level as well as a micro level. Because if we had not done the metrics to see what is the overhead that is being added by TCP, how does it stand in the current world? Because earlier the entire bandwidth, the connections were slow. But now if you are having 1 gigabit connection all the way up to your home, you are able to transact the same data lot more data than what you would otherwise send in a slower rate. And this is where the overheads of communications in terms of RTT tries to weigh in as a higher cost. And now we have to reconsider how we would want to use them or minimize these overheads. Nonetheless, when we used to try to do the UDP and brought in QUIC, it also has its own share of challenges, especially when we say QUIC is no more a network stack that's coming with the kernel, but it's an application layer stack. That means on one end, you have given a flexibility to build variants of QUIC protocols at the application layer and then adapt it for different applications. Two, the essence of trying to do things a lot more, like if I have multiple connections that I open, I would be doing the same aspect of like congestion control, flow control in each of the process independently. And this is where the overheads also start to creep in. And essentially, there were also the measurements that were done where it was shown that because Quick uses UDP and UDP was less of a utilized service, the stack in the network was not optimized for UDP at all, and that meant you would spend up a lot more overheads in processing the UDP packets. So all of these essentially meant that Quick started to have a high CPU usage. And also, we spoke earlier about the offloads that were possible to the network card, like if I want to do the encryption offload, checksum offload, all of those were supported by NIC, which were done by the TCP, and the kernel stack would then use the offloads of the hardware. But now with Quick, now you are in the user space, so it becomes a lot more challenging to say how I can really utilize these offloads. And this also means that now you are doing all of this computation on the CPU, which ends up having high CPU usage. So if you have noticed, when you use Chrome, most often you will end up having Chrome utilize large portion of the CPU, and that's because the variant that underlying, if it is having a lot more quick connections, it would start to see higher CPU usage. And when you want the data to be written to the user space, there are also the optimizations that were brought in to see how you can directly access the data right at the application layer. So we spoke earlier about the DPDK and map mechanism. So the same now hold fit for Quick. And in essence, if you see the other side of the opportunity, we see that Quick makes gluing this as a transport and application layer protocol for any of the applications that we want to build with a DPDK kind of a framework, it makes a very ready fit. And Quick has evolved a lot more than what it started in the early 2015s to where we stand into 2023. And Quick now is no more an acronym, but an IETF standard, and it was standardized in May of 2021, where the series of RFCs put forth by the Quick working group resulted in, like I said, RFC 8999 for vendor-independent properties of Quick, RFC 9000, which essentially describes a UDP-based multiplexed secure transport and how it is, what's the protocol aspects, how it is going to be built, and 9001 detailing about the TLS to secure Quick and why TLS 1.3 for Quick, and 9002 for Quick loss detection and congestion control schemes. And several of the additional extensions were brought in terms of how the HTTP workloads would often use, in terms of leveraging the header compressions like QPAC that you would use for the HTTP, and HTTP3 in itself, a new variant that you would want to support for the faster HTTP connections. So all of these have been standardized in the very recent times, and Quick has a very strong way forward also in terms of looking at the newer aspects that we want to build, especially like the load balancer, multi-path support, version negotiation, and many more aspects are currently still being discussed actively and are on the path to get standardized. And we have tried to basically summarize Quick in a very nutshell, but there is a lot more beyond what is being covered in this. I encourage you to go look at the RFC 9000 at the least to get a good understanding and grip on Quick.